We said the time crystal will solidify at 3:05. So we are 1 minute away from crystallization.
Sounds good. Sounds good.
Okay, so I think I have gone ahead and muted all except you, Norm. So you should be able to speak, so that way we can control the sound level. I would like to start by welcoming everyone to the first AQT virtual colloquium. We had our colloquium series running before the COVID outbreak, so I hope everyone is doing well and safely sheltered. And it looks like I think we will be in this mode of operation for some period of time. So I think this is a good way to start the series up again. In particular, we have a colloquium today. We will not have one in June because we have scheduled our stakeholder or sort of AQT update meeting for the month of June. So we will do that and then resume and pick up the colloquium series in July. So it is a tremendous pleasure today to have Norman Yao with us. Norman Yao joined the physics department as a professor at UC Berkeley in the summer of 2016. He received his AB degree summa cum laude with highest honors in physics and mathematics from Harvard University. After completing his PhD at Harvard, he began his postdoctoral work at UC Berkeley as a Miller Fellow. Norman has received many awards, including the Radcliffe Institute Captain John Fay Prize, the Deborah Ginn Award for Outstanding Doctoral Thesis Researcher in AMO Physics, the NSF Career Award, the Sloan Award, the Packard Fellowship, and the APS George E. Valley Prize. So it is a tremendous honor to have Norman Yao as our colloquium speaker today. Take it away, Norman. And if any of you have their mic unmuted, please mute it aside from Norman, because we hear the little ring, so they may be distracted. Thanks, everyone.
Excellent. Thank you so much. I think everyone can see my screen right now. So I don't have the box up where I can see people in case they're raising their hand, just so that I don't cover part of my screen. So really, I think I already emphasized this, but really, please ask questions. Feel free to just interrupt me, and I think that will. I'm sure there will be lots of people that share your questions.
Yeah, and during the talk, as Norman was saying, during the talk, please just go ahead and unmute yourself and ask the question. And in the question and answer period, you will use the raise hands feature to help us out. So I'll moderate that, but during the talk, if there's a question, just yell it out as Norman said. Please go ahead.
That sounds amazing. It's a wonderful pleasure to be here. I hear that I'm the guinea pig for this, the first online AQT colloquium, and it is also my first Zoom talk, so hopefully this runs smoothly. So today I'll be trying to tell you two stories about basically two different aspects of quantum information. One focused on understanding how fast quantum information can move, and another focused on really stopping quantum information from moving at all and seeing where that takes us. So these are kind of, in some sense, two sort of diametric opposites, but they'll both be kind of centered around thinking about dynamics of quantum information. So I've tried to really contextualize both of these studies and tried to give a sort of broad introduction. This work that I've been doing for a little while with a couple of my graduate students and theory collaborators shown here. And there's been some really productive and really nice experiments together with Irfan's group and Chris Monroe's group, which I'll mention in turn. So let me start by trying to give a little bit of context. So one of the ways to think about the first topic that I'll talk about is really in terms of a classic question that people ask in the context of condensed matter, which is that there's been, for the last half century or so, a tremendous effort at trying to understand and classify different phases of matter. And traditionally, I think in the sort of usual Landau-Ginzburg paradigm, we think about characterizing phases of matter by the pattern of their symmetry breaking. But more recently, there has been a really beautiful kind of advent in the language of quantum information, where we've really started to think about characterizing phases of matter by patterns of entanglement. And the emphasis I want to place here is that most of the time, we're often thinking about low temperature behavior. So oftentimes for Hamiltonian systems, we ask, what is the phase of matter in the ground state? At t equals 0, what exactly is the pattern of symmetry breaking that characterizes that phase? The two topics that I'll talk about today kind of diverge from this very traditional notion of condensed matter, where we're thinking about low energy, long wavelength properties of physics, but really we're going to be thinking much more about dynamics and much more about high temperature physics in both of those cases. So the first part of my talk, just as a little bit of a roadmap, I'll try to convince you that more and more there's a sort of well-defined notion for saying that one can not only classify phases of matter in terms of ground state properties, but that one can also take a Hamiltonian and classify its dynamics. So what I mean there is that we usually think about a Hamiltonian and we say, as I said, what is the physics of the ground state? But we know that the Hamiltonian itself is also the driver of dynamics, right? It's the driver of time evolution. And what I hope to convince you a little bit is that these days there's a reasonably sharp intuition for thinking about how to define and classify the quantum information dynamics that come out of different types of Hamiltonians. So part one, I'll try to show that there's a quantum circuit, an interesting quantum circuit, especially in the context of the AQT testbed, that will allow us to distinguish between different types of quantum information dynamics. So it'll allow us to classify different Hamiltonians in terms of the type of information dynamics that those Hamiltonians drive when time evolution happens. The simplest way to think about that is in terms of how fast quantum information can move around and how fast quantum information can thermalize, and that's kind of the intuition for part one. In part two of the talk, it'll be the exact opposite. We'll ask ourselves if we kind of are able to prevent the dynamics or thermalization of quantum information, what can we get ourselves? And in this context, I'll try to show another thing that's very, very relevant to the experimental thoughts within the testbed, that periodic driving can be a very, very powerful tool to take us into phases of matter that are really intrinsically non-equilibrium. And there's a question here whether or not we can realize these in some of the systems that the testbed is sort of pushing towards. Good. So let me just start with a short outline for part one. I'll start by trying to introduce and give some intuition for the fact that there are many, many different classes of quantum information dynamics. Then what we'll do is we'll work through a couple of natural diagnostics that one might naturally think about using to distinguish between these different classes. And we'll kind of emphasize that, some of these diagnostics that one felt were particularly natural are also challenging in other respects. Then in the main body of part one, I'll introduce a particular quantum circuit. So it's a digital quantum circuit where the goal is to really think about teleporting a quantum state, but doing so kind of well beyond the way we usually think about it when we learn it in sort of Nielsen and Trong, but in a very much more many-body context. And what I'll try to show is that this particular digital quantum circuit allows one to really, in some sense, disentangle scrambling, the behavior of information dynamics, from extrinsic stuff like decoherence. And more importantly, that it actually allows us to distinguish between different types of scrambling. And that's the particularly important thing. Along the way, I'll mention sort of two small-scale experiments in collaboration with Irfan's group and with Chris Monroe's group. Good. So let me start by, with everyone on the same page and just trying to give some intuition for what people mean in the literature when they talk about quantum information scrambling. In some sense, it's kind of a rebranding of a very, very simple idea. And the idea is that if we start with a very, very simple initial state, it turns out that if we time evolve under a many-body Hamiltonian, and that many-body Hamiltonian is reasonably generic, that the complexity of that initial state grows as a function of time. There are two pictures to understand and think about this complexity of growth. In the Schrodinger picture, the most natural intuition is, of course, we start with a state. So I can start with a product state where we imagine having sort of n different qubits. Those qubits are represented in blue. And what I mean is that the state, the initial state of the system, is just a tensor product state of a state on each of those different qubits.
Norman.
Yes, David.
for that statement, you're supposing the system is closed.
Yes, 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 yes. We'll talk about sort of, you know, how to distinguish between like intrinsic dynamics and extrinsic stuff, but absolutely. For now, we're going to think about a closed quantum system and then just, you know, internal dynamics under Hamiltonian evolution. Good. So that's yeah, exactly. It's a super important question. So as the system undergoes time evolution under a Hamiltonian, literally we think about this step as e to the minus iht, we say that the system scrambles. And all that means from the perspective of, you know, first year quantum mechanics is that entanglement forms between these different degrees of freedom. And at the end of this, you know, or at some later time, it turns out that the entanglement means that now there's a highly non-trivial entangled state that's where there's entanglement between these different qubits. And that's really, at some basic level, what we mean when we talk about quantum information scrambling. Of course, there's another picture that it turns out will be a little bit more helpful for the purposes of this talk, which is thinking about the dynamics of operators. So, of course, dual to the Schrödinger picture is the Heisenberg picture. And the Heisenberg picture, we like to think about the dynamics of operators instead of initial states. And here, in the Heisenberg picture, if you started, for example, with, let's say, V is some Pauli operator defined on an initial qubit, then as the system undergoes time dynamics, what we mean by scrambling is that the operator basically spreads as a function of time. And what that means is that the weight of the operator under time evolution basically gets more and more spread out over more and more degrees of freedom in the system. And this kind of operator spreading is in some sense what we mean in the Heisenberg picture when we talk about information scrambling. But in some sense, these two pictures are identical. So what I mean by increasing complexity up here is really, in some sense, if you're familiar with thinking about things from a sort of condensed matter stat-mechy perspective, really we're thinking about effectively something that looks like thermalization. So information about this initial state is effectively, you know, moved into non-local correlations that become harder and harder to access locally as a function of time evolution and effectively become irreversible if the Hamiltonian is complex enough. So that's kind of the basic idea of scrambling. And let me emphasize that you're all extremely familiar with scrambling, and we can already distinguish that there are different types of scrambling, different types of information dynamics for different classes of Hamiltonians in maybe the simplest context. So what I want people to think about now is imagine a one-dimensional system of spins. Could be qubits. So one-dimensional system of spins, you can think about these as either Pauli operators or spin operators, so totally relevant to transmons. And let's imagine ourselves restricted to basically a very, very simple kind of nearest neighbor Hamiltonian geometry. And I claim that you're already extremely familiar with the fact that even in this very simple 1D spin chain, there are different flavors of Hamiltonians from the perspective of dynamics. So again, not asking questions about low energy physics, but asking questions about how the Hamiltonian drives time evolution of such a 1D spin chain. The simplest and perhaps the most well-known / easily solvable version of a Hamiltonian is the transverse field Ising model or the XY model. So this corresponds to nearest neighbor interacting spins. This would be sort of sigma x interactions plus sigma y interactions between nearest neighbors. It turns out this type of a Hamiltonian falls under the category where it's both integrable, so there are many, many integrals of motion in the system, and also free in the sense that the scattering between excitations in the system is very constrained. In addition to integrable and free systems, there are also integrable and interacting Hamiltonians. So again, the number of conservation laws in such a 1D spin chain is extensive, but the scattering is no longer very, very simple. And that's why there's no free description. So the classic model of a 1D spin chain that falls into this category is a Heisenberg model. So it'd be sort of sigma I dot sigma I plus 1 nearest neighbor interactions. In addition to integrable Hamiltonians in both of these contexts, when one adds disorder to the system, one can get localization effects. So in the XY model plus disorder, for example, we talk about the classic phenomenon of Anderson localization. In the context of the Heisenberg model, which is the integrable and interacting system, if one adds in disorder, one has the famed many-body localized system that's been studied a lot in the last kind of decade and a half or so. And finally, there's perhaps the most generic type of Hamiltonian that lives on such a one-dimensional spin chain is something that, at least in this talk, we'll kind of think about all three of these terms, thermalizing, chaotic, and scrambling, as kind of synonyms for each other. But so a classic example of a Hamiltonian that falls into this category is the so-called mixed field Ising model. So nearest neighbor Ising interactions and a transverse and longitudinal field in the X and Z directions. So what I'm trying to emphasize here is really that in already a very, very simple geometry of a 1D array of nearest neighbor qubits, there's many, many different classes of Hamiltonians from the perspective of dynamics, in addition to from the perspective of low energy ground state physics. So I've mentioned that there are sort of 5 flavors, and these are maybe 5 that we're hopefully sort of generally pretty familiar with, at least things that we kind of are familiar with in the context of stat mech and condensed matter. More recently, there's been the advent of a new class, so it's now 6 flavors of quantum information scrambling, and this has come to fall under the moniker of fast scrambling. There are kind of very, very few models that exhibit this, but the one that's kind of most well known and found in the literature is something known as the Sachdev-Yeh-Kitaev model. I won't go into very much detail about this particular model, but it turns out the model is more or less an all-to-all coupled system of interacting Majorana fermions. Those are the degrees of freedom psi I here, but it's not particularly important for us to think about that. The emphasis here in terms of this fast scrambling is really that this model, in terms of its physics, ends up at low energies being dual to a gravitational theory in 1+1 dimension. And that's really cool. It's kind of one of the first examples that kind of helps us think about this sort of ADS-CFT correspondence, but allows us to sort of have a Hamiltonian formulation where the dual is some gravitational theory, although albeit a very, very simple one. And it turns out that one thing that people have been very actively trying to understand is how to distinguish the quantum information dynamics of this type of a model from all of these other types of model. And that's the sort of connection that I'll try to build upon today. So in some broad sense, I think part 1 of the talk is really, it's really something that's kind of where the topic is broadly sort of the intersection between high energy physics and quantum information science. Good. So I've kind of tried to introduce the fact that there are these different types of Hamiltonians in very simple systems that in principle you expect to have different dynamics. So a natural question at this stage that one can ask is, how would you expect to experimentally or theoretically in numerics distinguish between these? So probably many of you who are familiar with the disordered physics side of things immediately think to something called entanglement entropy. So let me just make sure that everyone's on the same page. For those who aren't familiar with entanglement entropy, it's a super simple idea. The basic intuition is to cut a system in 2. What we mean by that is you take a state of a full system, could be a density matrix in the most general context. You trace out, for example, half of the system, and you ask about the sort of remnant entropy between the half of the system that's left over with the half of the system that you traced out. So if you end up having, for example, a product state, the entanglement entropy is very low because I can make a cut where there's no entanglement across the degrees of freedom on the left and the degrees of freedom on the right. On the other hand, if you have a very entangled state, making this cut, there's many of these kind of entanglement bonds that I've drawn here as arrows that are kind of cut, so then the entanglement entropy ends up being large. It turns out that it is true. Entanglement entropy is extremely powerful, and what I'm plotting here on the y-axis is the growth of entanglement entropy as a function of some normalized time in a Hamiltonian system. So truly, we start with a product state, and we're time evolving under these 5 different or 6 different classes of Hamiltonians that we wrote in the previous slide. And those of you who are familiar with disordered systems will immediately see the virtue of entanglement entropy. You can see that the blue curve is the dynamics of entanglement entropy in models that are so-called Anderson localized. So these are disordered models, which where the disorder lives on top of an integrable and free Hamiltonian. And the statement is that the entanglement will grow for a very short period of time, then will saturate for all further times. This can be distinguished between the many-body localized type Hamiltonians, which was another box in the previous slide. Here, one finds that in some sense, the early time entanglement entropy growth looks very, very similar, but at late times, one sees the difference. One sees that in the many-body localized system, the entanglement entropy actually grows as a logarithm of time, whereas the Anderson localized case basically saturates. You can see it's a log because the y-axis is ln scale and the x-axis is log scale. And then, of course, it turns out there are thermalizing Hamiltonians, and these thermalizing Hamiltonians end up having entanglement growing as a linear in time. So typically for these systems, S grows as T. On a log scale, it'll be very nonlinear and very quickly shoot off. So you might say, well, that's pretty good. It seems like, entanglement entropy is indeed distinguishing between a couple of these different dynamical classes. The problem is that all of the other things that are not localized Hamiltonians basically fall into this thermalizing category. So the growth of entanglement, all of these systems basically looks very, very quick, and it's only the sort of localized systems that one can distinguish using entanglement entropy. So while powerful, it turns out entanglement entropy is not quite enough to be able to distinguish all of these different classes of scrambling dynamics. So let's move on to going back to this kind of picture that we had. As I emphasized, operator spreading will be our friend throughout this talk. And so when we have this initial operator, I emphasize that scrambling is really thought about as the spreading of this operator in space as a function of time. So if you look at the Heisenberg time evolution of this operator, it will have weight, even if it was initially on a single qubit, it'll have weight on many qubits after a sufficient amount of time. And usually we think about, for example, the spreading of local operators being something, illustrated by a light cone, for example, here. And a natural way that we might think about scrambling is looking at this operator and asking, for example, at some late time, what is the support of the growth of this operator on a subsystem at a very, very distant scale. So looking at, for example, in some sense, the overlap or the perturbation of this operator on a different operator P at a distant scale, which is far from the initial Q. And it turns out the diagnostic for looking at this type of operator spreading, the simplest diagnostic in some sense, is something known as an out-of-time ordered correlation function. So the correlation function should look pretty weird to you. It's not that easy to measure, but effectively, it looks like we're basically taking the, applying an operator at time t equals 0 on a system, then time evolving forward in time, measuring the operator q, time evolving backwards in time, measuring the operator p, and time evolving forwards in time, measuring the operator q again. Just to give a little bit of very, very simple intuition for why this kind of evolution backwards in time is kind of useful and necessary. The idea is that, in this initial operator, as the initial operator basically expands, you can apply a perturbative operator at some late time somewhere far from the initial site. And when you time evolve backwards, you can basically ask a super simple question, which is whether or not this kind of fully expanded operator over here rephases to its initial simple operator over here. If it does, you know that basically the other operator that you applied at some late time doesn't impact the dynamics. And if it doesn't, you know that the other operator over here has basically perturbed the system in a way such that it prevents this system from coming back. And that sort of is the intuition that the system has sufficiently become chaotic or is sufficiently scrambled. So it turns out that these types of out-of-time ordered correlation functions have been super useful in the kind of the high energy literature. And there's been a really, really beautiful series of works coming from the groups of Maldacena, Shankar, and Stanford, where they basically show that in a generic system, or in quite special systems that are fast scrambling, excuse me, that the decay of the OTOC, if one looks at 1 minus the OTOC, that grows as an exponential. And it turns out people like to think about this exponential, this lambda, as the sort of quantum version of the Lyapunov exponent. And what Maldacena, Shankar, and Stanford showed is that in a very, very generic set of assumptions, there's a bound on how fast quantum information can spread in any quantum mechanical system. So let me emphasize that for a second. There's a conjectured bound on the rate of quantum information spreading in any system, and that's basically bounded by 2 pi over beta, where beta is the inverse temperature scale of the system. It turns out the most interesting case, of course, is trying to ask about whether or not there are Hamiltonian systems that actually saturate this bound. And the fast scrambling Hamiltonian that I wrote, this kind of class 6, the SYK Hamiltonian, is known to precisely saturate this bound. So there's particular interest in sort of thinking about the physics in that context. Any questions at this stage? I hope I'm not going too fast, but if there are any questions, please let me take a second and ask for them. Okay, I hear tacit.
Feel free to unmute your mic if you want to ask a question.
Oh yeah, that's a good point. Your mics are muted by, yeah, exactly, that's right. I'll take this as tacit consent for now. So this really harkens exactly to David's question from a little bit earlier. If you look at this plot over here, and you look at the dynamics of this out-of-time ordered correlation function, in an experimental system, this out-of-time ordered correlation function decays as a function of time, and here the decay is caused purely by a closed system internal Hamiltonian dynamics. But for the experimentalists in the audience, I'm sure none of you are unfamiliar with decays of correlation functions. And indeed, this out-of-time ordered correlation function would also decay because the system is not closed. So we have a very, very well-defined question, which is if I had a truly closed system with a Hamiltonian, its scrambling dynamics will cause a correlation function to decay. On the other hand, if the system is not perfectly closed and it's a little bit open, that openness will also cause the same correlation function to decay. So there's a very natural question, which is how can one distinguish the dynamics of scrambling from the dynamics of some extrinsic physics like decoherence? And what I'm showing here is a particular experiment from Chris Monroe's group using a very, very small trapped ion system, where they're basically tracking the OTOC as a function of time. And it turns out these two different curves, one of them is actually the purple curve, is basically running a digital quantum circuit where we expect scrambling to happen. And the orange curve is running a digital quantum circuit that's a very complicated version of the identity. And you can tell that in both cases, the OTOC decays. And it's very hard to distinguish, at a qualitative level to say that, if you saw some plot like this, it'd be very hard to say whether or not the scrambling was truly coming from closed quantum dynamics or coming from, non-openness of the system. So it turns out that what comes to rescue is that this out-of-time ordered correlation function is maybe not the right measurement to make, but that there is a different digital quantum circuit to run that allows one to really nicely distinguish between scrambling and decoherence. So it turns out this is the circuit that I've drawn here is a circuit that is originated from Benny Yoshida and Alexei Kitaev in an archive paper from 2017. There's a series of works, one by Adam Brown et al. From the Google group. I don't remember, I think the exact title, but it was something like Quantum Gravity in the Lab. And another really, really pretty work coming from Ping Gao and Daniel Jafferis, where they analyzed nominally a different circuit from the Yoshida and Kitaev circuit at least the context where they were thinking about the circuit was very different. It turns out, unbeknownst to Brown and Gao and Jaffrus, the circuits were presciently the same. So actually, all three circuits end up with a little bit of careful manipulation to be exactly the same digital quantum circuit. So let me take a little bit of a step back before introducing this precise quantum teleportation circuit and emphasize how to think about this, or how I like to think about this. So, people in high energy like to think about this as sort of an algorithm or a digital quantum circuit that allows one to tell things about black holes, essentially, allows one to tell things about fast scrambling Hamiltonians that are dual to gravity. But I think about this in a much, much different way, maybe coming from a kind of more AMO/quantum optics background. So coming from that background, I want to start by reminding everyone what a conventional quantum teleportation circuit looks like. So if you go to, I don't remember the chapter, but if you go to Nielsen and Chuang and you look at quantum teleportation demonstrated by various groups, the intuition is that the two parties that would like to teleport a quantum state initially must share some resource, and that resource is entanglement. And the form of that resource is an EPR pair in this case. So Alice has her half of the EPR pair that she shares with Bob. And if Alice wants to teleport a qubit psi over to Bob, what she does is she makes a measurement, a joint measurement on her half of the EPR pair and her extra qubit that she'd like to teleport. She classically communicates the result of that measurement. I mean, this is unsurprising. I mean, this is everyone. I know this is introducing something that everyone knows, but I still want to emphasize it because it's kind of, the quantum teleportation circuit that that people are thinking about is very relevant to this. She classically communicates the results of that joint measurement. From those results, Bob knows the rotation, the proper local unitary to do on his own qubit, and after doing that, he decodes and basically gets out psi. So the circuit that I'm going to draw, so this is not exactly how it's presented in these papers on the previous slide, but this is, there's no difference. This is a slight manipulation of the circuit, but actually the circuit, it's really identical to the circuit that those people are thinking about. So what I'd like to emphasize is we should really think about the circuit that people are talking about within the context of quantum gravity and these sort of SYK models as a many-body generalization of the same conventional quantum teleportation circuit. So now, instead of Alice and Bob each having a single qubit that's in an entangled state, now we have Alice and Bob each having many qubits. So I mean, I've drawn 5 qubits here, but we should really think about this as a many-body system. The state, the entanglement resource between Alice and Bob, is again a shared entanglement in the initial state. So there's no gates, no quantum gates that happen. There's only classical communication afterwards, which means that all of the entanglement resources must be in the initial state. And it turns out that in the most generic setting, this initial state is something called a thermofield double state. But let me give you a simple limit that you should think about and not worry about the thermofield double state specifically very much. In the limit where we take the infinite temperature limit for the thermofield double state, this is equivalent to Alice and Bob sharing n EPR pairs instead of one EPR pair. So imagine that each of these qubits, qubit this one and this one are an EPR pair, this one and this one are an EPR pair. The thermofield double state basically is a finite temperature generalization of this, where you basically have a weighted version of this kind of entanglement. So again, what is the goal of this many-body teleportation circuit? Well, let me explain how it operates first. Alice would like to teleport a state. In this case, it could be a single qubit or multiple qubits, and she would still like to teleport it to Bob. But now, the goal is that Alice can teleport in the qubit, can move in the qubit on a world line over here, but eventually she'd like to make only a very, very small number of measurements on qubits that are not the initial qubit that she moved in over here. And that requires you to run a many-body unitary over here. So the circuit functions as follows. Alice would like to teleport this qubit. she performs a many-body quantum circuit, a unitary. This can be either digitally decomposed or analog. And we should really think about this in some sense, in the most generic case, as time evolution under a Hamiltonian. Then she measures, no longer jointly, she measures in the Z basis a very, very small subset of qubits that don't overlap with the qubit that she was initially hoping to teleport. She classically communicates the results of these measurements, and Bob now performs U star, so a different version of the unitary, then kind of does the same type of a decoding over here by performing local rotations that are conditioned on the measurement result that Alice got. Then he does another run of the unitary and decodes this state psi. So you can really see that the way I'm thinking about this is really that there's more or less almost one-to-one correspondence between this sort of, conventional quantum teleportation we learn about in textbooks and this kind of new circuit, but it's sort of a many-body generalization of this. But there's shared entanglement. We want to teleport. Alice has to make a measurement. She does classical communication. Bob has to do a conditional rotation based on the measurement results before ultimately decoding the state. So the first thing I want to emphasize is that although people call this a many-body teleportation circuit, this is a terrible way to move quantum information around. You would never use this type of a circuit in a quantum repeater. This would never be like the way to build up a quantum network. But this particular digital quantum circuit, which I think can be run on the testbed and other kind of quantum simulation platforms, is super powerful because it can teach us about the scrambling nature of Hamiltonians. But I've never mentioned a Hamiltonian when I explain this circuit. So the connection to a Hamiltonian and the intuition for thinking about why this particular circuit can tell us something about the scrambling nature of the Hamiltonian is that I'd like you to think about the unitary here as being time evolution under a Hamiltonian. So the real intuition for this part of the talk is that in the very beginning, I tried to give you some sense that there are all these different classes. We wrote down 6 classes of Hamiltonians on that slide that in principle have very different information dynamics. And I said that it's hard to tell those information dynamics apart from each other. It turns out that this many-body teleportation circuit, as far as the community I think knows and understands, is the best way to distinguish between the quantum information dynamics generated by those different classes of Hamiltonians, and that's why it's particularly powerful. Any questions? This was maybe a kind of weighty slide, but a particularly important one. Good, okay. Hopefully everyone's following. So it turns out that that one thing that we can say
Actually, I have a sort of a general question.
Yes, please.
Which might not be here nor there, but do you gain any extra security by doing many-body teleportation rather than the simple one?
It's amazing. That's such a good question. I can't even say that's such a good question. Yes, the point is that you definitely gain security in the sense that, and in some sense, the way to think about that security, David, is that scrambling basically, as we've already said, encodes local information into very, very non-local correlations, such that any local measurement basically can't really destroy that particular piece of information. But at the same time, usually like we think it is very secure, but the problem is that, and in some sense, scrambling, Hamiltonians that scramble or something like the SYK Hamiltonian is like a really, really good, way to kind of encode information. So you would think that it kind of maybe makes a very, very natural building block for something like quantum error correcting codes. And people have thought about this very actively. People have asked the question, can you take this notion of scrambling, which delocalizes information initially, and that's generally what error correcting codes do anyways, and build new codes out of it? The problem is that scrambling encodes really well, but it also makes decoding really, really difficult. And in some sense, you can think about this many-body teleportation circuit, David, as precisely a decoding algorithm for a scrambling. right? In some sense, it allows you using local measurements to basically decode this state that was initially scrambled by this unitary, but it's hard. Like you had to share all this entanglement resource. So I think that the answer is yes, encoding definitely happens, but decoding is commensurately hard. So that at least from the perspective of useful encoding, I'm not sure that scrambling gives you anything very natural.
When you have quantify hard, you mean it has problems with scalability?
Yeah, so for example, yeah, that's right. So I think that the proper statement here is that decoding scrambling basically is, I think, exponentially sensitive to noise. So for example, you might say, the encoding is really, really good, so you really don't lose this information, but it turns out that if you don't decode it perfectly, you also don't get back the exact information that you started with. Good. So one thing that's true about the circuit, but won't be the most interesting thing, is that teleportation occurs if and only if the Hamiltonian scrambles. So if we have the unitary, where we think about it being driven by time evolution, teleportation within this many-body circuit will only occur if the Hamiltonian scrambles. But we already have emphasized that there are many different Hamiltonians that scramble, but that they scramble differently. So that's something that we'll basically come back to. Maybe the most important thing we'll come back to at the end of this first part of the talk. But let's return to what started to motivate us to think about this circuit in the first place. And the motivation that I emphasized is that the OTOC, this kind of out-of-time ordered correlation function, was not super useful in terms of looking at scrambling because it didn't allow us to distinguish between decoherence. In addition to allowing us to eventually probe the different types of Hamiltonian scrambling that can happen, it turns out this type of a teleportation circuit also allows one to distinguish between scrambling even in the presence of decoherence. So a little bit of a couple of equations, but they'll be painless. So instead of thinking about my time evolution as unitary, when I think about, for example, decoherence, the natural way to think about this time evolution is to think about the dynamics as being generated by a quantum map, for example, or quantum channel. This quantum channel Q, you can see here, has some dynamics that are indeed unitary. And here I've done the simplest thing, which is basically to add in some probability P of having a fully depolarizing channel act on the qubits in question. It turns out the really nice thing is that when you put in this particular quantum channel into the teleportation circuit, you can actually quantify the channel decoherence in a very, very simple way because the output fidelity of the teleportation knows about how much decoherence delta is happening within the system. More importantly, what Benny and I proved is that you can bound the actual OTOC for a closed quantum system by looking at the teleportation fidelity of an open quantum system in this particular many-body teleportation circuit. Let me really emphasize this again. All you have in your experiment at your disposal is to run your experiment in an open quantum system. But the fidelity of the open quantum system teleportation, if you run this many-body teleportation digital circuit, bounds the OTOC in the closed quantum system. So in the absence of decoherence, it bounds it. So of course, bound means that, decoherence means that you can no longer know what the actual OTOC would have been if you purely had unitary evolution, but you know that there has to have been at least so much scrambling because of this particular bound. Good. So there's been a couple of super fun collaborations. One in an all-to-all connected ion system of 7 qubits with Chris's group, and another with Irfan's group, where they've been working on a really, really beautiful kind of experimental upgrade to work with superconducting qutrits. And this kind of increase in the local Hilbert space allows one to have a lot more flexibility in terms of the geometry that one needs to have to basically look at scrambling. It turns out that here's an example of the quantum circuit that was run in Irfan's experiment. At the end of the day, they did a conditional measurement a joint bell pair measurement, after which they looked at the teleportation fidelity conditionally. It turns out that for those of you who are kind of a little bit familiar with this, this joint particular measurement can actually be made into a deterministic algorithm by embedding a couple layers of Grover's search within this circuit. So in the case of trapped ions, what I emphasized before is that the OTOC, for example, can decay in a system that either exhibits scrambling or a system that decoheres, but it's very hard to distinguish the two. But here, the emphasis is that if you look at the teleportation fidelity in this many-body circuit, you find that the case where there's really no scrambling happening means that the teleportation, you cannot get many-body teleportation if your digital quantum circuit does not scramble. On the other hand, there's OTOC decay in the purple dots, and here you see the teleportation fidelity increases above the kind of lower bound, above the sort of, trivial case of 50% teleportation, which is exactly the same as a random guess. So this really shows that the many-body teleportation circuit allows one to distinguish between scrambling, closed system Hamiltonian dynamics, and extrinsic coupling to an open system. Just one thing that I want to emphasize about the superconducting implementation is that in addition to seeing the same physics in terms of the teleportation fidelity, there's also a super nice ability to do tomography to basically really distinguish between kind of things that are local gates, things that are entangling but not fully scrambling, and things that are scrambling. So what's represented here in the simplest way is that if you think about an operator, for example, on a single qtrit, and you ask what happens when you do a gate, either that only acts on that qtrit, or an entangling gate that acts on two qtrits, or a fully scrambling gate that acts on two qtrits, the situation with a fully scrambling gate is really that this initial operator is delocalized into all other combinations of Pauli operators within this two qtrit basis. So this is really, kind of a nice visualization of this intuition of operator spreading in the context of scrambling. So a little bit of moving forward, though, and I think maybe a super interesting next set of experiments that would be fabulous to do. And the emphasis here is that, both of these experiments check to see if U scrambles, but not how it scrambles. And that's really important because in the sort of Hamiltonian, where the slide where I showed these various Hamiltonians that have different types of scrambling dynamics, what I was emphasizing there is that these Hamiltonians can move quantum information around, but they can move quantum information around in very different ways. And in particular, one would really, really like to be able to distinguish between a system that's fast scrambling. So you should think about this fast scrambling system as, I think about it these days as maybe one of the hottest topics that people are thinking about in the context of high energy. And this fast scrambling system is really something where people think about the dynamics as being dual to the physics of black holes. And we'd like to distinguish between that type of a scrambling dynamic and a generic Hamiltonian, for example, just a simple spin chain that thermalizes, or a generic chaotic many-body Hamiltonian. It turns out up to now, before this kind of a many-body teleportation circuit, my claim is that there was no way to really easily distinguish between these two types of dynamics, fast scrambling dynamics and generic scrambling dynamics. So let me emphasize what one would generically expect for a scrambling system, for a generic scrambling system in terms of the teleportation fidelity within this many-body circuit. I emphasized when I was describing the circuit that the teleportation can only happen if the system scrambles. In both Irfan's experiment and Chris Monroe's experiment, we weren't doing things in an analog fashion, so we were really doing a digital gate set, and this digital gate set was made to fully scramble information. But in some sense, there was no well-defined notion of time. And here I want to emphasize that I'd like to think about the x-axis as being time because I want to think about time evolution under a Hamiltonian. If I have such a Hamiltonian, when would you expect teleportation to happen? Well, you'd expect teleportation to happen after the system scrambles. And we know that the system scrambles at late times. So once all of the degrees of freedom in the system have basically been mixed together, you expect the system to have scrambled, and that's true. So you expect that the teleportation fidelity on a many-body circuit is basically high at some time t beyond a scrambling time, which I've called t star over here. So that's the simplest expectation to have. If you have a generic many-body Hamiltonian that scrambles, at late times, you should expect that the teleportation fidelity is high. It turns out what we've kind of discovered, and we have a really nice kind of understanding for this, is that this fidelity as a function of time is non-monotonic, which is super cool. So it tells you that actually at timescales before the scrambling time, you can teleport. At timescales after the scrambling time, you can teleport. But somehow there's a parametrically long intermediate timescale between which you cannot teleport with high fidelities. Let me emphasize that this type of a plot is made for the many-body teleportation circuit, where the initial entanglement resource between Alice and Bob is this thermofield double state at infinite temperature. Super important, which means that the initial entanglement resource is basically n EPR pairs shared between Alice and Bob. On the other hand, it turns out that if you take a fast scrambling Hamiltonian, so something like the Sachdev-Kitaev model, and you ask about what its fidelity looks like as a function of time, you see something dramatically different. You see that the teleportation fidelity is low at early times. You see that the teleportation fidelity is low at late times, but the teleportation fidelity is high at intermediate times, precisely around the scrambling time. There's a beautiful gravitational interpretation of this, which one can find in either the Gowan, actually, I think Gowan Jaffrus is the nicest paper to see that interpretation. But it's really qualitatively distinct from a generic many-body scrambling system, in the sense that here, you really cannot teleport either at early or late times, but there's really something very, very non-trivial about the nature of the scrambling dynamics that allows, the name that people gave to this is phase size winding or phase winding, but allows phases in the many-body system to wind in a way that kind of really, really nicely allows information to pass from one side to the other. And this is also what people mean when they think about this as so if you hear in talks these days, people talking about traversable wormholes, this peak is precisely information moving through the traversable wormhole. So let me emphasize that the generic scrambler that I've drawn here, I've said that it's, has basically a high teleportation fidelity at early times and also at late times. And the scrambler that I'm thinking about, that I have in mind when I'm drawing this kind of a schematic plot, is really a zero-dimensional random unitary circuit. So what that means is basically, in this case, a digital quantum circuit. This is something that I've been thinking about in the context of the text bed in particular, where one allows, here one has arbitrary connectivity between different qubits or qutrits, and the time scale is really the depth of this quantum circuit. And one really does expect for, I think it's probably, I think one can see this qualitative feature already for a system with maybe 40 to 50 qubits in it. So I think it's really something that one could imagine exploring near term in the testbed. Good. So yeah, just emphasizing that this sort of
Norman, sorry.
Yes, Jean.
Just quick question. So what is G and P here? I missed this point.
Yeah, so G and P is right. So G, it turns out, is something that lives in this particular Z1. So it turns out you end up doing a rotation that's e to the I G, the value of the measurement that was made by Alice over here. So G basically kind of controls how quickly basically these oscillations you find over here, but it's basically something that lives in this decoding unitary that one does on Bob's side. And P is even harder to explain. It's it's an encoding that we had to do. So P, in order to see this kind of a distinction, it turns out you end up wanting to encode this single qubit in actually multiple qubits. And in this case, we're encoding it in P qubits. It'll be a little bit more clear once I show you the numerics, but if it's unclear, please ask the question again.
Thank you.
Yep. Good. So let me just emphasize that this schematic plot that I drew is real. I mean, one can't actually analytically calculate anything in these contexts. There are, many body time dynamics. I don't know how to do any of it, but turns out one can do numerics. So here we're doing simulation on n equals 10 million qubits. This should immediately surprise all of you, but let me emphasize that the circuit that we're doing is a Clifford circuit. So the Clifford circuit basically means that, kind of Pauli strings get mapped to Pauli strings, which means you only need to track very, very simple evolution. Here, these numbers are as follows. I'm trying to teleport 1 qubit. Alice encodes this 1 qubit in 1,001 qubits out of her 10 million. So it's a super tiny number. Eventually, Alice measures k number of output qubits. In this case, it's 1 million output qubits, still much smaller than the actual number of qubits in her many-body system. And Bob decodes using the measurement result of these k million answers. So, let me emphasize, you get really nice numerics here, but you can already see the qualitative feature for much smaller systems. And you see that the teleportation indeed basically has sort of high fidelity initially, and then ends up going through a parametrically large period where teleportation is basically a half, it's a guess. And then at late times, as promised, basically it asymptotes something well above 90%, but there's basically some finite size corrections that happen over here. So the teleportation value is not quite 1, but it's clearly high for all times after the scrambling time, which is what I promised. It turns out, without getting into too much detail, the physics of this type of teleportation is fundamentally distinct from gravity. And this is something really, really cool. So I want to emphasize something. This is something I find really, really remarkable about the kind of Yoshida-Kitaev circuit, and also the circuit that Brown and Ping and Gaffris proposed. It's the same many-body circuit here, right? I'm emphasizing that the circuit that you run in the experiment does not change. The thing that changes is basically the Hamiltonian that goes into the unitary. In certain cases, you'll get this. In cases that are really related to gravity, you'll get something that looks like this. In the gravity case, the physics is related to some sort of phase winding that's that's really remarkable and beautiful, and that's very deeply related to this lambda equals 2 pi over beta, saturating the bound on chaos. But I want to emphasize that from the same circuit, you get 2 very different qualitative signatures of fidelity as a function of time. And moreover, the microscopic physics that explains why teleportation is allowed to happen here and here, as opposed to in the gravity context, is different. And we now understand what happens in this non-gravitational context. It ends up being related to the size of operators. And there's a beautiful understanding where it turns out basically that the size of operators is growing as a function of time. It ends up hitting a finite, at the end of the day, you only have a finite size system. So at some point, the operators will basically be the full system size. The standard deviation of operators is also growing as a function of time, but eventually peaks and comes back down, because the standard deviation is really sort of, if you think about operator distributions, it's how much variance I have between different sizes. And at some point, once all of the operators get larger and larger and larger, there's less and less variance to be able to have. And the figure of merit that ends up sort of characterizing this type of a fidelity in the many-body circuit is basically the size of the operator distribution. So at both early times and late times, the size of the operator distribution is small, and that's why teleportation can happen. Whereas at intermediate times, because of this peaking of the variance, the operator distributions are extremely broad, and that's what pushes down the teleportation fidelity. So just a little bit of summary.
I'm just giving you a quick time check. We're at the 1 hour mark, okay?
Interesting. That's interesting. Okay. Well,
Because you don't want the audience to unscramble very rapidly.
yes, that's true. No, that's true. That's true. Okay. I mean, that's okay. Let me, well, okay. I think this was the main thing I wanted to get through anyways. But so I'll take my time, but I probably won't get to part two. I can send people slides if they're interested in what I wanted to say in part two. So what's the summary of the physics of scrambling that can be probed if we're able to implement such a digital quantum circuit in the testbed, for example? It turns out that if you have a generic thermalizing system that's in 0D, so you really allow for arbitrary connectivity at each depth, at each step between different qubits, then you expect for the single qubit case to basically get this kind of early time and late time teleportation with a parametrically large intermediate regime of no teleportation. It turns out if you now have a generic system that's 1D, so the difference would be a digital circuit where you allow only nearest neighbor connectivity, you no longer have what I think is particularly cool, which is this feature of this kind of intermediate non-monotonic behavior, high, low, high. You still have oscillations, and these oscillations will be very, very nice to be able to understand the many-body scrambling. And at late times beyond the scrambling time, you will still be characterized by the fact that there will be a plateau that is high fidelity. In the case of multiple qubits, let me emphasize that the early time behavior is kind of the same. You can still teleport multiple qubits with relatively high fidelity. But if you try to do this experiment, I think this would be something very cool to see. You get a very, very strong signature that you're doing this many-body teleportation correctly, because as you scale up the number of qubits you try to teleport, it turns out the late time fidelity goes down exponentially. And if there was an ability, either digitally or there was some analog system that could do this, to be able to simulate something where the scrambling dynamics had the Hamiltonian dynamics associated with fast scrambling had this gravity dual, then you would be able to see this really, really characteristic feature where you have this kind of intermediate high teleportation fidelity surrounded by sort of low teleportation fidelity, and where this high teleportation only happens at the scrambling time. So one thing that I think is particularly interesting to think about, and which I've thought about a lot, although to be honest, I haven't made much progress on, is whether or not this type of a bump can be seen in more generic digital circuits, or whether it really, really relies on the Hamiltonian being dual to gravity. So I've been trying to kind of think whether or not one can define kind of models that are approximately dual to gravity, and whether or not one can get, suppressed versions of this feature without, suppressed versions of the feature, so it's not really fast scrambling, but maybe features that are still kind of analogous to gravitation without necessarily being exactly dual to a gravitational action. I think let me just summarize this part of the talk. This will be the whole talk, I guess. But I hope I've convinced you that there is, there's been the advent of a particularly interesting circuit to run from the high energy perspective that's kind of been thought about as a many-body version of a quantum teleportation circuit, or actually, and that's the way I like to think about it. And I'd like to emphasize that this circuit has a couple of very nice virtues. One, it allows one to disentangle sort of closed system dynamics from open system dynamics. Two, it allows you to tell something about what types of errors happen in your circuit. So it allows you to learn whether or not depolarization or dephasing is sort of the dominant noise source. And finally, perhaps most importantly, it allows you in very, very qualitative ways to distinguish between different types of scrambling, and in particular, those types of scrambling that are dual to fast scrambled models that look like the physics of black holes. Okay, with that, let me stop. I'm already a little bit over, and let me thank you for your attention.
We thank you, Norm, and we are sort of digitally and physically clapping for you, as we would in a colloquium talk. So the paper is open for questions. We'll have a brief question and answer period. Depending on how many folks we get, I think let's start with just unmuting yourself if you have a question, and if there's too many of us, we'll use the raise hand feature. So open for questions.
I hope
In
I hope this is a sign of clarity and not a sign of
Sure.
everyone's been lost since the third slide.
I have one question for you, Norm. When you have the Z1 and the Z2 measurements for the many-body teleportation circuit,
Mhm.
how many of those measurements would you need to make as a fraction of the total number of qubits? And can they be any combination of the qubits coming out?
Yeah, so one, they can be any combination because precisely in the sense that you scrambles, sort of all of these different legs are kind of the same. And the answer to that question is that there is a correction to the fidelity, basically, that scales with the number of measurements that you make over here. But I think, so if I'm not mistaken, the correction scales extremely well. So, if you measure something like 1% of the output qubits over here, that's already enough to get a teleportation's fidelity in a sort of I think a small scale system, something like 50 qubits above 90%, or 90, I think maybe even 95% in that case. So it really is that, the measurements over here are just kind of giving you a little bit of an inkling about what the heck has happened in this U. And then it's really this kind of initial entanglement resource that allows you to sort of do the right conditional things to basically reconstruct psi over here. But you can think about, I think the right answer is basically, let's say between 1 and 10% of qubits to be measured here, and then the same number of conditional rotations on Bob's side.
Thanks.
Yep.
Okay, other questions from Norm? Maybe I'll ask one if time permits here. You talked about sort of larger numbers of qubits and that giving us various dynamics that you could sort of numerically simulate, showing different regimes of where fidelity should be high or low. If you had a system that was much smaller, let's say of order 10 quantum elements, are there distinct signatures to be had there that sort of distinguish between these different timescales and mechanisms of scrambling?
You wouldn't be able to distinguish basically this intermediate peak, I think. So this dip, is really important. Like you basically need, if I'm not mistaken, a separation of scales that's basically n, the number of qubits, is much larger than p, the number of encoding qubits, or is it n much larger than k, n much larger than log k, much larger than log p, much larger than g. So you have a series of basically kind of scales in the problem that need to be sort of satisfied in order to see this particular kind of intermediate regime of parametrically low teleportation fidelity. But even for a system, I have to say I haven't really done the numerics for 10 qubits or 10 qutrits very, very carefully, but I'm pretty sure that you should be able to see basically something like a 1D system that basically looks like this. And you should be able to, the key is that you should be able to track this oscillation as a function of log G, and you should be able to still really clearly see that you're really seeing this kind of many-body teleportation effect.
Got it. Okay, any final thoughts or questions from Norm before we wrap it up today? Okay, with that, we thank you very much, Norm, for giving us this very helpful talk, for helping us understand the sort of the pulse of high energy physics, scrambling. And again, for the audience, the next talk we'll have will be on the 10th of June, and that'll be our stakeholder meeting. It will be more of an extended function where we talk about the testbed capabilities and current projects. So be on the lookout for that. And if not, I wish everyone a good afternoon. Be well and be safe, everybody. Bye-bye.
Thank you so much, everyone. Bye-bye.